This is SpaceTime Series 29, Episode 71, for broadcast on the 15th of June 2026. Coming up on SpaceTime, the expansion of the universe is still accelerating after all, mysterious cosmic signals finally explained, and what made last week's New England meteor incident so rare. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has confirmed that the universe is continuing to expand at an ever-accelerating rate under the force of dark energy, and that means we're heading for a cold, dark and empty fate. The findings, reported in the Journal of the Monthly Notices of the Royal Astronomical Society, debunks last year's study, which suggested that the strength of dark energy was weakening, and as a result the rate of cosmic expansion was either slowing down or may even have stopped completely. The authors of the original study had suggested that the methods used to measure the universe's expansion using Type 1a supernovae, exploding stars, which all blow up with roughly the same amount of energy and hence same luminosity, was fundamentally flawed. But the new study's lead author, Phil Wiseman from the University of Southampton, says the re-evaluated data shows that the universe is behaving exactly as expected. He says last year's revelations were the result of a scientific misunderstanding rather than a flaw in the universe itself. That means the original and well-accepted measurements were in fact fine, and our current understanding of the fate of the universe remains robust. Wiseman says by proving the original measurements were correct, astronomers can now get back to trying to understand what dark energy actually is, rather than wondering whether it exists at all. The original discovery of the accelerating expansion of the universe, made by Adam Rees, Brian Schmidt and Saul Perlmutter, won them the Nobel Prize for Physics in 2011. If the 2025 claims had been true, it would have dismantled their findings, as well as nearly 3 decades of astronomical progress. The authors found that when they calibrated these supernovae, accounting for the different host environments and populations, the evidence for cosmic acceleration remained remarkably consistent. The 2025 study had claimed that as the universe aged, these supernovae had different maximum brightnesses, tricking astronomers into thinking the cosmos was accelerating when it was actually slowing. However, the new Southampton study found the error lay in how the age of these stars was estimated. They proved that the previous findings incorrectly assumed the age of a galaxy was the same as the age of the star that exploded in it. The authors also say the 2025 paper failed to account for the mass of the host galaxies, a standard correction used in modern cosmology to prove accuracy. The 2025 findings led to speculation that instead of the universe ending up in a big freeze, or worse, a big rip, it might end up in a steady state, or possibly a big crunch. A big crunch is where gravity eventually overcomes the outward expansion of the universe, resulting in the cosmos ultimately collapsing back in on itself. That could have led to another Big Bang, followed by another big crunch, followed by another Big Bang, and so on. The steady-state universe would have seen the outward expansion eventually slow down and glide to a stop. But the new findings show dark energy is continuing to accelerate the expansion of the universe. That means we're in for a big freeze, the heat death of the universe, where eventually all the galaxies will move so far away from each other they'll disappear beyond what's called the cosmic horizon. So far away that even at the speed of light from these distant galaxies can never reach us, consequently leaving us alone in the dark empty cosmos, where the stars will eventually run out of fuel and one by one turn off, leaving only the cold, dark blackness of space. It means star formation will probably end in about 100 trillion years from now. Black holes will then begin to evaporate at about 10 to the 40 years, and by 10 to the 100 years, known as the Google, yes, that's where the word Google comes from, the universe will be nothing more than a uniform soup of subatomic particles and photons, with a temperature hovering just above absolute zero. An even worse fate would be the so-called Big Rip, And that would see the power of dark energy continuing to increase. Consequently, the expansion of the universe would continue to accelerate, depending on the existence of phantom energy, an accelerated version of dark energy, and that would see not only galaxies disappear beyond the cosmic horizon, but star systems would be torn out of their galaxies, planets would be torn away from their host stars, and ultimately atoms would be ripped apart from each other, and eventually their electrons, protons and neutrons would be torn away, leaving an ionized plasma, which theoretically could even see the quarks inside protons and neutrons ripped apart from each other. But that wouldn't take a Google years. That could happen as soon as 150 billion years from now. This is space-time. Still to come, mysterious cosmic signals that have baffled scientists finally explained. And what made last week's New England meteor incident, which we reported on, so rare? All that and more still to come on SpaceTime. Astronomers have discovered that dead stars known as white dwarfs, which are located inside binary star systems, are a primary source of mysterious signals from deep space known as long-period radio transients. Long-period radio transients are cosmic pulses of energy emitting from just a few remote regions of the sky. The new findings, reported in the journal Nature Astronomy, provide the best evidence yet for these unusual cosmic events which have been baffling scientists for years. Using the Australian Square Kilometre Array Pathfinder radio telescope in outback Western Australia, the authors detected a white dwarf, the core of a dead sun-like star, dragging material off its larger but less dense companion star. And as this stellar material spirals into the white dwarf, it produces powerful bursts of radio waves and X-rays in a cycle that repeats every 1.4 hours. The discovery now provides astronomers with a natural laboratory to examine extreme physics. The study's lead author, Covey Rose from the University of Sydney, says it's the first time anyone's pinpointed the origin of these signals, confirming the source to be a cataclysmic variable in a accreting white dwarf star. Rose says long-period radio transients have puzzled astronomers for years. Only a dozen or so have ever been found, and their origins have always been unclear, until now. The newly identified system, named ASCAP J1745-5051, consists of a white dwarf, a dense stellar remnant with roughly the diameter of the Earth, but with a mass closer to that of the Sun, paired with a larger but lower mass red dwarf star, about 1/10 the Sun's mass. These two objects orbit each other extremely closely, completing a full orbit in just over an hour. As material from the less massive star is drawn towards the white dwarf, it heats up and emits X-rays. Now, at the same time, interactions between the two stars' magnetic fields generates regular radio bursts, resulting in a signal which occurs at very specific intervals. Rose says these emissions are all tied to the orbital motion of the system. But interestingly, the radio and X-ray signals don't peak at the same time, and that tells scientists they're being produced in different regions of the system. The authors found that the radio emissions likely originate from the magnetic fields of the two stars meeting and interacting with the charged material being ripped off the companion star by the white dwarf, resulting in highly beamed bursts of radiation. Long-period radio transients were originally thought to be slow-spinning neutron stars, pulsars. However, current models suggest that neutron stars rotating this slowly shouldn't be able to produce such signals. So the new discovery strengthens an alternative explanation, that at least some of these mysterious bursts come from systems of two stars involving white dwarfs. Some similar objects had been linked to binary systems before, but this is the first observation that clearly shows both of the stars and the accretion process itself in action. The system's also only the second known long-period radio transient to emit regular X-rays, and the first where the cause of this regularity has been confirmed. ASCAP J1745-5051 could act as a reference point for understanding other long-period transients. You see, the system gives astronomers a way to decode the signals. Rose says it could help determine whether other long-period transients are more like pulsars or like white dwarf systems. In that way, it acts like a sort of stellar Rosetta Stone, the famous archaeological stela discovered in Egypt that allowed scientists to finally translate ancient Egyptian hieroglyphics. The discovery also provides a unique opportunity to study extreme plasma physics and magnetic interactions under the sorts of conditions that simply can't be replicated here on Earth. Rose says these natural laboratories will allow astronomers to test our understanding of how matter behaves in a strong magnetic field under intense gravitational forces.
The goal here was never to target white dwarfs or anything like that. What we've been looking at is finding these astrophysical transients, things that go bump in the night. And I think what's really unique about this research is that we've been able to figure out, as you said, that it is a white dwarf binary system that is producing these otherwise mysterious radio bursts. These are long-period radio transients. So historically, the first kind of clear repetition that was seen in radio signals was discovered from pulsars, which are these rapidly rotating neutron stars that produce bursts of radio light every time they spin around, normally on orders of every few milliseconds or seconds. And long-period transients kind of looked very similar to pulsars when they were first discovered, but tended to repeat on timescales more like minutes to hours, hence the long period name.
Now, once you realised it was coming from a white dwarf, this is a sun-like star that's reached the end of its life and shed off its outer layers, exposing its core.
Yeah, so with pulsars, we're still trying to figure out the exact mechanism, but it seems to be that every time they rotate, we see a burst of light that's kind of a beam of radio light coming from near the poles of the pulsar. Kind of like the North and South Pole.
Like a lighthouse shining in the night.
Exactly, Stuart, yeah. And with long-period transients, I should say that some long-period transients still might be, when it all comes out in a few years as we learn more and more about these things, some of them may be sort of weird and wacky pulsars, but at least for the binary ones, what we seem to be finding, and I think what was really great about this discovery is we were able to figure out that the point that the radio light is coming from is actually where the magnetic fields of the white dwarf and its companion star meet. The X-ray signal, which also repeats in this same 1.3 hour period, which is the same as the time it takes for the stars to do an orbit around one another. The X-ray seems to be coming from accretion, which is basically as the white dwarf, which is more massive, pulls material, the gravitational forces from the companion, as that material rapidly accelerates down towards the white dwarf surface, it gets heated up and ionized, electrically charged. And that is what we believe is producing the X-ray signal that we see that's repeating, as well as some additional ultraviolet light that we detected from the system.
You base these findings on one very specific white dwarf binary. Tell us about the system.
So this is a system that was discovered as a weird radio transient. There wasn't a lot of information available on what it was. Sometimes radio astronomers will find a weird thing in the sky. We'll say, oh, that radio point wasn't there before. And when you compare to other catalogs of, let's say, optical telescopes that are in space, like the Gaia satellite, you can see, oh, this is a known star or this is a known supernova from some other catalog. In this case, there wasn't a lot of information to go on, so it was kind of a mystery to build up all these little scraps of information to figure out what it was. So we used Gaia, an optical telescope, to figure out that there was some faint optical source there, and that could help us understand it. It wasn't a nearby or bright star. We used other telescopes to figure out, like I mentioned, that there's ultraviolet emission and there's X-ray emission. But I think the real crucial part to figuring out that it was a white dwarf binary system was getting optical spectroscopy. So basically breaking down the rainbow of light that's coming from the system. And what was really cool when we did that was that we saw there were these signals, these kind of characteristic signals of hydrogen emission and helium emission. And these tend to come at a particular wavelength. This is kind of a fundamental thing based on the properties of hydrogen and helium, so it should be the same throughout the universe. And there's a set wavelength of light that we should see this hydrogen and helium signature at. So what was crazy was that we were noticing the signal shift back and forth in wavelengths, basically a Doppler shift that was happening. And that is what let us know that we were looking at not just a white dwarf, but a white dwarf in a binary.
A low mass binary.
Yeah, exactly. So there are characteristic colors and temperatures that you expect for different stars. So, for example, you could look at a star like our sun, and that's kind of a very average star, and that's not by accident. We do tend to compare the other stars in the universe that we discover relative to our sun. So if you imagine our sun as kind of like an average point, you could have a star that is, let's say, much colder than our sun, and that would have a lower brightness. It would also have a redder color, basically just like you can imagine when you look at a flame from your stove or from a campfire, you see the red hot bit, but the kind of white hot is a hotter temperature. And so in astronomy, we have not just red to white, but we also have blue, right? We have stars that are bluer in color, so to speak, which means that they are hotter. So white dwarfs and extremely hot and bright stars are often quite blue in their color temperature. These are things that tend to have temperatures of the order of tens of thousands of degrees. And then on the colder or redder end, you have things that have temperatures of maybe a few hundred or a few thousand degrees. So in this system, we were able to see that there are two things. We have something that has a temperature that's very blue and has a temperature of several tens of thousands of degrees, and that's the white dwarf. And then we also have something separately that is of the order of a couple thousand degrees, and it's a lot redder, and that's the low mass companion. So by piecing together all the different information that we have, we were able to figure out that we have these two different unique stars in the system.
You used ASCAP for that, didn't you?
Yeah, so ASCAP was critical for the initial discovery. All the work that I've been doing over the past few years has been finding weird and wacky things using ASCAP, which is an incredible telescope located here in Australia at Inyarimana Ilgari Bundara, the CSIRO Murchison Observatory in Western Australia. And ASCAP is a great survey instrument. It covers huge parts of the sky, and it kind of gives us a map of all the things that are there. And by seeing what's there, we can figure out what's changing, we can figure out what's appearing. So the initial discovery was made with ASCAP, and then I did follow-up observations using both MEERKAT, which is a radio telescope in South Africa, and also ATCA, the Australia Telescope Compact Array, which is a lovely telescope here in New South Wales, where I'm calling from. And ATCA is just incredible for kind of doing long tracks, really precise measurements to see not just is there a radio source there that we're seeing in the sky, but how is it changing over time?
All right, you've got one. That's lovely. But really, to be comfortable, you'd want to find a few more examples of this, wouldn't you?
Yeah, well, this has been the tricky thing with long period transients. So the first official discovery was, I think, only in 2022. So only about 4 or 5 years ago were we first finding these weird LPTs, as they're called. And most of them have been found in a region of our galaxy that's close to the galactic plane, which is kind of a much dustier area. And that dust tends to obscure a lot of the optical light that we would otherwise measure from space. And that has meant that it's been kind of difficult to figure out what is producing, what systems or what objects are producing the radio light. And so what's great about this system is that while in the past we've had things where we'll have radio and optical but no X-ray, or radio and X-ray but no optical, or just radio. In this case, we have the radio, the X-ray, the optical, and even ultraviolet. And by forming kind of a more complete picture with this one LPT, it's going to allow us to use it as a kind of a Rosetta Stone to decode maybe past discoveries, but also future discoveries. As we keep discovering more and more of these weird transients, we'll be able to maybe understand a bit more about them.
What's likely to be the ultimate fate of this white dwarf, red dwarf binary? Are we likely to see a nova, maybe even a supernova ultimately?
Yeah, that's a really good question. I think in some cases we can see type 1a supernovae when you have a star that's accreting onto a white dwarf, and if there's too much material that it gets accreted onto it, you can end up with that white dwarf exploding as a type 1a supernova. But I think what's also quite interesting about this class of accreting white dwarf binaries that we've been learning recently is that they can actually have this really strange phenomenon called a period bounce. So the period refers to the orbital period, right? You start with, let's say, a main sequence star like our sun, or slightly less massive, and it's orbiting around with a white dwarf. And as they get closer and closer together, the orbital period gets lower and lower. And around the 80-minute mark, what we often see is that the white dwarf has stripped so much material, through its gravity, it's pulled so much material from its companion, that the companion is no longer a main sequence star like our sun or a low mass star, but is a brown dwarf, which is kind of like a missing link between high-mass planets and low-mass stars. And when you have a brown dwarf, that can't keep doing the nuclear fusion that keeps stars going. And so what will happen at that point, this period bounce that I mentioned a moment ago, is when the system stops orbiting closer and closer together, and then suddenly, instead, the orbits get further and further apart. Basically, the stars will drift away. So the end state for systems like this could, in some cases, not necessarily be a supernova, but instead they slowly drift apart, and you've gone from having a massive star and a white dwarf to a massive star and a brown dwarf.
Brown dwarfs come into existence either by planetary-sized objects getting bigger and bigger and bigger, or alternatively by red dwarfs losing too much mass through fusion and simply burning off most of their mass. So this is a third way we can get a brown dwarf.
Yeah, exactly. I'd always thought of brown dwarfs as failed stars, which seems a bit harsh, but it's quite interesting to think about this new way for brown dwarfs to form.
That's Covey Rose from the University of Sydney. And this is SpaceTime. Still to come. Last week we reported on a meteor that rocked the afternoon spring skies of New England. Now it turns out that was a very rare event. And later in the science report, a new study has confirmed that sugar-sweetened drinks increase your risk of 2 types of liver cancer. All that and more still to come on SpaceTime. In last week's SpaceTime, we reported on a meteor that rocked the afternoon spring skies over New England. Well, it now turns out that was a very rare event. Residents reported a loud explosion, sending emergency services scrambling to try and understand what caused the blast that shook buildings across Massachusetts and Rhode Island. It turns out the explosion was the double sonic boom of what was thought to be a meter-wide meteor entering Earth's atmosphere in the skies above the New Hampshire border with Massachusetts, north of Boston. Later, NASA was able to confirm the event was a meteor travelling around 121,000 kilometres per hour, which likely airburst with a force of around 300 tons of TNT, fragmenting at an altitude of about 60 kilometres, with the remains falling into Cape Cod Bay. But it now turns out, with the addition of extra data, that meteor was much larger than previously estimated, possibly almost double the size, and at least 6 tons in mass. Robert Lansford from the American Meteor Society says this type of meteor is rare for its size, its brightness, and the fact that it happened during the day. He says a lot of light has to be produced by an extraordinarily large meteor to be visible in the daylight skies. Lunsford says, for those witnessing the encounter, it was a once-in-a-generation event. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study has shown that sugar-sweetened drinks appear to increase the risk of 2 types of liver cancer, while artificially sweetened drinks don't. The findings, reported in the Journal of the American Medical Association, found that even a 1 beverage a day increase in sugar-sweetened drinks increases the risk of the most common type of primary liver cancer. The new research analysed data from 11 previous studies, which included more than 1.5 million adults, in order to assess the liver cancer risk of people drinking sugar-sweetened drinks compared to those consuming artificially sweetened beverages. The authors found that while sugar-sweetened drinks were associated with increased liver cancer risk, artificially sweetened drinks were found not to increase the liver cancer risk. Scientists have discovered a new species of fish swimming in the warm tropical waters of the Great Barrier Reef. It seems the bright orange-red, hairy, long-snouted ghost pipefish is a new species that had actually been hiding in plain sight among the colourful corals for years, but was often confused with other ghost pipefish. The reason for the confusion is that ghost pipefish are masters of camouflage and can easily meld into the background. These close relatives of seahorses and sea dragons often closely match the colour of their surroundings and develop skin filaments that look like algae and coral. The findings, reported in the journal Fish Biology, show that the new species, now called the hairy ghost pipefish, has actually been known about for years, with divers and underwater photographers uploading images and videos to social media. However, marine biologists noticed a consistent morphological difference between this fish in the photographs and museum specimens they had examined, and so decided to investigate. They analysed mitochondrial DNA from 2 specimens collected from the Great Barrier Reef and compared them with DNA records of the rough ghost pipefish. And they found a 22% genetic difference between them, strong evidence that they were in fact looking at 2 different species. A new study has found that living with cats won't worsen asthma or allergies in children. The findings, reported in the journal Frontiers in Allergy, looked at more than 30,000 children between the ages of 4 and 17. The authors studied asthma severity and lung function in children who already had asthma in homes with at least 1 cat, and compared that to children with asthma living in households with no cats. And they found there was no association between asthma outcomes and the presence of cats in the household. They found that moderate to severe asthma occurred in 9.6% of cat-exposed children and 10.1% of non-cat-exposed kids, while asthma attacks occurred in 3.3% of cat-exposed children, but 3.5% of non-exposed kids. A new study warns that nearly half of all American consumers act on guidance from social media influencers or AI tools, often without any fact-checking or professional input. The findings by the Academy of Nutrition and Dietetics also found that 80% of Americans struggle to tell fact from fiction when it comes to nutrition, often driven by clickbait, viral wellness trends, and pure pseudoscience. The skeptic's Tim Mendham says the results show a serious problem.
A lot of people believe influencers. That's why they're called influencers. It's a huge industry these days. Every second person has their little TikTok clip somewhere. They're making ads, I noticed, for TV in the shape of a TikTok influencer thing just to make people feel comfortable. They're saying a survey has said that nearly half of US consumers on guidance from social media influencers or AI tools, often without fact-checking or professional input. People often listen to this, and there's all sorts of things on TikTok. There are people who are representatives of alien civilizations on TikTok. There are people who say, well, everything conceivable, basically. You can find it somewhere on TikTok. And they're very influential. There was a story a number of years ago of someone claiming that if you swallowed cotton wool balls, it would actually help your digestion or something. Joke.
Wasn't there one about Tide? Take some dishwashing liquid or something?
Yeah. Well, hydroxychloroquine and all sorts of things that were sort of bleach was sort of promoted. And these were just influencers and things and people doing stuff. But what started off as a joke with the cotton balls, it ended up being people sort of following it, and they can actually damage their health very badly. Anyway, what this survey says was that 8 in 10 Americans, which is 80%, struggle to tell fact from fiction in nutrition, and they're driven by clickbait, which is sort of saying, I can cure you so-and-so, viral wellness trends and pseudoscience. These people, sort of half of them, are not interested in following up and finding out sort of from qualified sources. They'll believe the influencer, or they'll go online, as you said, Google, Dr. Google, or any sort of things, and saying, what's the cure for this? And they get a response from an AI bot or an AI sort of app of some sort or another, and they believe it. That's a large number of people who act on totally unqualified advice coming from someone a young girl who looks nice, for instance, a young woman, etc., who looks attractive, etc., giving you health advice, pitching their latest cure they're selling. So what it is, it's not a fringe group. It's a large percentage of the population who are following these things, with the consequence of that, whether they have a condition or not, whether whether it's an imaginary condition or a real one, they're not getting the help they need. And that's a danger. That's a real danger. Therefore, people will continue to be sick, or they get sick by not getting proper treatment, or because they believe someone who has no qualifications just telling you in a nice voice that this is what you should do. Major issue that it's getting worse and worse and worse.
That's the skeptic's Tim Mendham, and this is Space Time. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to Space Time with Stuart Gary. This has been another quality podcast production from Bytes.com.